Hello to everybody. So here's what we're going to do, you guys. We are going to be looking at some different models, the transition state model and the collision model, but essentially what we're looking at are two different models for calculating K. All right, so let me finish writing that down. K, and we're talking about the rate law constant here, right? All right, so the first one is they have actually done things where they calculate K based on something called the transition state model. We're not going to calculate anything with this model, but the idea behind the transition state model is still important. And so here's the idea of that transition state model. This is familiar to you. If we were to graph like potential energy over the course of a reaction, you guys are super already familiar with, reactants, products, all of that good stuff. We've talked about, hey, there's a certain amount of energy, E sub A, you might need to add the activation energy to get that to react. But the whole thing, when they do the calculations for this, are based on something up here at the top of that little curve known as the activated complex. And this activated complex is essentially a transition state that we're looking at. So if I were to just compare that to, say, looking at a reaction, and let's say this reaction was 2BRNO, which reacts and decomposes into 2 nitrogen monoxide and a bromine, and this is an exothermic reaction. So here's my 2 reactants, and here's my products. Same axes on this graph. But up here, what I might find is there's a BRNO molecule and a BRNO molecule, and there's like some sort of like partial bonds that start to form here. And these bonds start to get really, starting to break apart. And so that is the activated complex with these partial bonds. Of course, one of the things we've also talked about is that if you have a catalyst, you quote unquote lower the activation energy, which isn't entirely true, but what we do is there actually with a catalyst is a new activated complex with the catalyst. And that activated complex actually exists at a lower energy state. So it's not that we've taken this one and lowered it. We haven't, but we've provided another energy pathway. It's lower. And so as a result, things are going to travel to the path of least resistance. Anyway, here's the thing. Calculating K from this, it's a whole bunch of complex calculations. They lead to really good results. We're not going to try to calculate it. It's sort of beyond the scope of this course. But I just want you to understand, this idea of the activated complex and having a new activated complex with a catalyst and things, those are all super important ideas in there as well. All right, so one we will look at with math is the collision model. And we've already addressed this a little bit. But the collision model is based on the assumption that molecules must collide to react. But we know not every collision is going to be a reaction. So here's the idea in the collision model. In the collision model, the reaction, let's call it the reaction rate, I guess. The reaction rate depends on 3 things. And we've mentioned these. But one is what's known as the steric factor. This is designated P. Why my thing is flashing a little bit. And what the steric factor means, it's the fraction of the collisions with good orientation. So I'm going to use the little example reaction that I have up here in order to kind of demonstrate that. So if you could envision, for example, if I have, my BRNO molecule if that two of them, if this one's traveling this way and this one's traveling this way and they hit each other, what we may end up with is a bromine and then some nitrogen oxide molecules. But if instead my BRNO molecule that's traveling in this direction hits another BRNO molecule that's oriented this way but traveling in this direction, we're going to get no reaction. They're not oriented properly for that to happen. So that's what this steric factor deals with, is how many of the reactions or the collisions actually have the right orientation. Number 2, collision frequency. Collision frequency is designated Z, and that's really just like, hey, are they hitting often enough? So this is the number of collisions in some given unit of time. And like we mentioned before in class, like the more collisions you have, the more likely you're going to have a reaction, and so your reaction is going to go faster. And then the third thing is I'm just going to actually call it what it is. There's not a fancy name for it, but it's the fraction of the collisions with enough activation energy, E sub A. And this is a designated F. So this goes along with that Maxwell-Boltzmann distribution chart or graph where we have, this is the number of molecules, let's say versus energy. And let's say we have at 25 degrees, this represents the molecules as they react. But let's say that if you have this more than this, you have enough activation energy to collide or to actually have a reaction occur. So what we're talking about is this kind of tiny proportion. And this goes back to this, right? So this is the amount of energy we're talking about, but we're representing it differently. Well, if we raise the temperature, this graph starts to flatten out. Like, let's say this is 45 degrees Celsius. But now, look what happens to the fraction of the molecules with enough activation energy. So that's what F is referring to. Well, if we put them together, our rate law constant is actually equal to P times Z times F. And so this is the rate law constant. Here's the issue. The steric factor and the collision frequency independently of each other are hard to measure. So these are actually combined and they're called A. And A is what they sort of generically call this frequency factor. So what this is it's looking at the number of collisions that are occurring, the fraction of collisions with good orientation over a certain amount of time. So it's just been combined. And then F is actually equal to E, like the natural log E thing, to the negative E sub A over RT power. So written another way, K is equal to A times E to the negative E sub A over RT power. So this starts to let us think about a few things. Like, remember that rate is equal to K times the concentration of our reactants raised to some powers, right? So this is the K we're talking about. And so some things that I want you to think about are, if E sub A is big, what does that mean is happening to K? So, if we have a big E sub A, but it's a negative exponent, right? So this is where it becomes a little more complicated to think about. But with a negative exponent, that means if E sub A is big, our F, our fraction, is going to be going down, right? And so if our E sub A is big, then, like, think about over here, right? Here's if we raise the E sub A, we have a smaller fraction that are able to actually react, which means K is going to go down. And then that's going to affect the rate. So you have to be able to kind of walk it backwards through that. Or, for example, if the temperature goes up, well, it's in the denominator of a negative exponent. If temperature goes up, that fraction is going to increase. That has the fraction that is going to end up reacting with enough activation energy. Well, great. That means we're going to have a bigger K and a bigger rate. So being able to think about those things is going to be important. So do please consider that. All right, so this, we can use it to find K if we have activation energy, if we have RT, but it's probably not going to be as useful that way. So instead, we're going to change that, and we're going to take the natural log of both sides, and if we do, what we end up with is the natural log of K is equal to the natural log of A minus E sub A over RT, because we're taking the natural log of E. Then we're going to rearrange it, and I'm going to rearrange it purposefully. I end up with natural log of K is equal to negative E sub A over R times 1 over T plus natural log of A. And the reason I'm doing that is because scientists don't love exponents. We like lines. Y equals mx plus b. So what that means is if we were to graph this, and we graph the natural log of K versus the inverse temperature, we would get a graph that looks like this, with this as the slope. So slope is going to be equal to negative E sub A over R. This is an energy, activation energy, so this is going to be my 8.314 joules per mole K version of R for this. So if you graphed how the rate law's constant changes with temperature, because they do, you can actually find the activation energy. Or if you're interested in finding, wait, what's a frequency factor, right? What's A? That's your intercept to this graph. So you could actually find the frequency factor. Now, we need one more version of something that's going to be more helpful to us. So one thing right now I want you to see is K will change if the temp changes. Right? So why is that again? Oh, wait, because look, if the temperature changes, K is going to have to change. So K is going to change with temperature changes, which means if we know the K at one temperature, if we change the temperature, that's not going to be valid anymore. So we're going to derive something much like the Clausius-Clapeyron. If I know, in fact, here is that equation. If I know at one temperature, I will get 1K. Oh, look, I made it a 2 because I'm already prepping us for what we're going to do to this. And if I was at a different temperature, I would have a different K. So we'll call this T1. So at temperature 1, I've got rate law constant 1. At temperature 2, I have rate law constant 2. If I actually subtract one from the other, I will get natural log K2 minus natural log K1 equals, these are going to subtract out from each other. And so I'm going to rearrange this, negative E sub A over R 1 over T2 minus 1 over T1. Should be starting to look a little familiar. I'm going to rearrange it one more time to the version we want. Natural log K2 over K1 is equal to, I'm getting rid of the negative sign, so I'm going to change that way those temperatures are. 1 over T1 minus 1 over T2. Bubble, highlight, star, blah, blah, blah. Not on the periodic table, you guys. But what this is a version of the Arrhenius equation Now, when I say a version of the Arrhenius equation, like what's the actual Arrhenius equation? Sorry, didn't tell you. It's this, okay? But that one's hard to deal with. So this is a version of the I can't talk, of the Arrhenius equation, but here's where it's helpful. If you know K at one temperature, and you change it to a new temperature, you can find a new K, assuming you know the activation energy. Or if you know 2 Ks and 2 temperatures, you could find the activation energy. That's another option for you. Obviously, consider the fact this is joules per mole Kelvin, so your temperature units do need to be in Kelvin. But this is great if you change to the temperature, and you will be encountering that where they give you the activation energy and they give you the K at one temperature, and you need to use that K to then employ its use in maybe some integrated rate law or something like that. All right, so that's what we needed to accomplish. Good job. Signing out.